All right, I want to work through the problem that you looked at in class on Monday at the end of class. So I gave you 10 minutes to work on this problem, and I want to work through it to give you an idea how I would approach this problem, go over some key points, and again, hopefully help as you're working on the problems that you're doing for class on Wednesday and as you prepare for the upcoming exam. Again, just to be clear, this is the problem that we're going to be looking at, right? You can see the IR, you can see carbon-13, proton NMR. All right, so that's the problem that we're going to be working on. It's labeled as problem 24. And unlike most of the problems that we have, we're given a molecular weight instead of a molecular formula. So that makes it a little bit more challenging, but hopefully we can work through that. All right, so let's take a look at this and see if we can figure out what's going on. So let's look at the IR first. We'll ignore the phone call. So the IR is going to tell us, essentially we have 3 peaks, right? So we have a peak at 2963, one at 2874, and one at 1738. Those two are from CsP3 to H bonds. All right, so just some nice hydrocarbon bonds. And then if we look at the 1738, hopefully we think very quickly that that is from an ester. All right, so we're thinking that we have something that looks like that. Let's just confirm that we have an ester. All right, so we can confirm in the carbon-13. So in the carbon-13, we have a peak, looks like it's about 173. And that definitely confirms that we have an ester. Right? There's no way that we would see a ketone or an aldehyde at that position. So we have an ester, which is really nice to know. That helps us know we have 2 oxygens in this molecular formula. We have 1 degree of unsaturation. It would be nice to figure out what the molecular formula is. So let's look at a couple of other pieces of information. In the carbon-13, we have 1, 2, 3, 4, 5, 6 peaks. So we have at least 6 carbons. We might have more if there's some symmetry. If we look at the proton NMR, if we add up the integration, we have 2 plus 3 plus 3 plus 6. So that gives us 14 H's. The other interesting thing is that we see there's 1 peak that integrates to 6, so that must be 2 CH3s there. That tells me that we should have 2 equivalent carbons. So that would lead me to believe, so this 6H, we have 2 equivalent CH3s. So that would lead me to believe that we would have 7 carbons because we have 6 peaks, 2 are equivalent. So I would guess that we have 7 carbons. All right, so my first guess at the molecular formula would be 7 carbons, 14 hydrogens, and then 2 oxygens coming out of the ester. So I would guess it's C7H14O2. So let me just see if that works. So 12 times 7 plus 14 plus 16 times 2, and that gives me 130. Right? So we hit the molecular formula, which is really important to get that nailed down. All right, if we look at this, we do our calculation of degrees of unsaturation, ignore the oxygen, CnH2n plus 2, right? We'd get C7H16, we have C7H14, so that's consistent with our 1 degree of unsaturation. We know that it's a pi bond in the ester. We've already figured that out, all right? So that's great. We've already extracted the information we need out of the IR. Carbon-13, we know we have some symmetry there. We know we have an ester. So now let's focus on the proton NMR. All right, if we look at the proton NMR, let's just list out the peaks. So at 4.1, we have a 2H quartet. And then we have a strange peak at 2.1, right? And it's really interesting and important for us to note that this peak just looks odd, right? So at 2.1, we know it integrates to 3H, but it looks strange, right? And it might be useful for us to think that perhaps there's some overlap there. So maybe this is from two peaks that are overlapping, because it doesn't look like a normal type of peak that we're used to interpreting. All right, let's move on. So there's a peak at 1.3. That peak integrates to 3H, and it's a triplet. And then we have a peak at 0.96H, and it's a doublet. All right, and what I would say is initially, let's just ignore that strange-looking peak that perhaps is from overlap, and let's interpret the other peaks so we can figure out what's going on here. All right, so let's work on our structural fragment. All right, and again, we're going to use our strategy of the black is going to be H's in the peak, and red is going to be neighboring H's. All right, so 4.1 2H quartet, so 2H again is going to be a CH2. If it's at 4.1, that clearly shows that it's deshielded, must be attached to an oxygen. All right, so there's the side of the ester where the oxygen is attached to a carbon group. And then the fact that it's a quartet tells us that it has 3 neighboring protons, so that tells us that it's a CH3. Okay? So that right there, we're done with half of the ester, because that's the O, CH2, CH3. All right, we'll find that CH3 in a minute. Or actually, we'll find it right now. If we ignore what's going on with this strange overlapping peak, the next peak we come to is this 3H triplet. That's got to be a CH3. And a triplet is it's next to the CH2. All right, so right there is that group right there. All right, so we've nailed down half of the ester. Right now we just have to find what's going on the other side. Right, so now we come to our 0.96H doublet. All right, so that tells us that we have 2 CH3s that are equivalent. They must be coming off the same carbon. And then if we look at the fact that it's a doublet, it must have that H in the neighboring position. All right, so this is our isopropyl group looking for common structural fragments. All right, so now we have to figure out what's going on with this strange overlapping peak. All right, so a couple of things that we know. All right, we know that we have half of this molecule already built. CH2, CH3, O, and we're not sure what's coming off the other side of the ester. All right, that CH3 is 1.3 3H triplet. The CH2, 4.1 2H quartet. Okay, we know that we have a CH. All right, so where is that CH? It must be part of this overlapping peak. All right, it can't be nowhere, so it must be there. So this is really helpful to us. That lets us know that of the 3H, one of them is that CH. Right? That means the other 2 H's must be part of a CH2 group. Okay? So where must that CH2 group be? If we think about the potential for structure here, it's clear that this CH, this isopropyl group, has to be attached to something, and it must be attached to the CH2 group that we have right here. All right? So what's going on here is we have 2 overlapping peaks. We can't see what's happening in terms of the multiplicity, but the integration and the fact that we know we have an isopropyl group in here help us figure that out. So that must mean that we have a CH2 attached to a CH and then to 2 CH3s. Okay? And again, just to double check this, the CH2 is going to be part of, we're just going to say it's 2H at 2.1, and again, it's overlapping. And then the CH is the 2.1 1H, and again, it's also part of that overlapping peak. And then the 2 methyls are at 0.9, the 6H doublet. Okay? So again, I think if we do these and we work through them very methodically, make sure that we're trying to go not just focus on one thing at a time, but really trying to extract information and confirm things, such as confirming the ester from the IR in the carbon-13. And then when we get to the proton NMR, really thinking about structure, what it tells us, what has to be true because of the fact carbon makes 4 bonds, and coming up with actual real structure. I think we're going to be able to do this. And again, we're going to get better with more practice. So I hope this is helpful, and we'll talk more about problems like this in class on Wednesday.